Imagine a particle approaching a wall. To our everyday eyes, the wall is an absolute barrier. If it is solid, thick, and impenetrable, no object, no matter how small or fast, should pass through it without extraordinary force. A baseball will bounce back, a beam of light will reflect or be absorbed, and a human cannot walk through it. Classical physics, the physics of Isaac Newton and the macroscopic world we inhabit, assures us that a barrier represents an ultimate limit. The energy an object possesses determines what it can overcome. A hill too tall to climb, a door too heavy to push, a wall too thick to pass through, these are inviolable. But in the strange, probabilistic world of quantum mechanics, this certainty dissolves. At the scale of electrons, protons, and other subatomic particles, barriers that should be absolute are, in fact, permeable. This phenomenon, called quantum tunneling, is one of the most counterintuitive ideas in physics. It tells us that a particle does not behave merely as a tiny solid object, but as something far stranger, a wave of probability, a cloud of potential locations, a blur of existence that can appear where, by all classical reasoning, it should not be. When a particle encounters a barrier, it does not simply hit it and bounce back. A part of its wave, like nature, extends beyond the barrier. Within that extension lies a non-zero chance that the particle will emerge on the other side, as if it had slipped through the wall without breaking it or using brute force. The origins of this idea are deeply rooted in the development of quantum theory in the early 20th century. Physicists were grappling with phenomena that defied classical explanations. Radioactive decay, for instance, was observed long before it could be understood. Particles were emitted from nuclei even when they did not appear to have enough energy to escape the electrostatic forces binding them inside. Similarly, electrons in atoms occupied discrete energy levels, and yet they somehow transitioned between levels in ways classical physics could not account for. The mathematical tools developed by pioneers such as Schrödinger, Heisenberg, and Dirac revealed a universe that was fundamentally probabilistic, where certainty gave way to possibilities and probabilities governed the behavior of matter and energy. To understand why tunneling is possible, it is necessary to reconsider the nature of a particle. In classical terms, a particle is a tiny point with a specific position and momentum, moving predictably along a trajectory. In the quantum realm, however, particles are better described by a wave function, a mathematical expression encoding the probability of finding the particle at a particular location at a particular time. This wave function is not merely an abstract tool. It represents a real aspect of how particles exist. When the wave function encounters a barrier, it does not abruptly stop. Instead, it gradually decays across the barrier, diminishing in intensity but never reaching zero entirely. This means that there is always a chance, however small, that the particle can be detected on the other side. The process is inherently probabilistic. Unlike throwing a ball over a fence, where success is determined by precise energy and trajectory, quantum tunneling has no deterministic guarantee. A particle may attempt to cross a barrier countless times, only to fail repeatedly, yet eventually succeed. The success of a particle in tunneling is governed by factors such as the height and width of the barrier and the energy of the particle, but it is never certain. This probabilistic nature challenges our intuition because, in our everyday experiences, objects behave predictably, obeying cause and effect with near-perfect certainty. The quantum world, in contrast, operates on chance, on waves of possibility that manifest into actual events when observed. Despite its counterintuitive nature, quantum tunneling is not just theoretical. It is real, measurable, and central to the workings of the universe. Early experiments confirmed its existence in the 1920s and 1930s, when physicists observed electrons escaping potential wells in ways classical physics could not explain. Later, tunneling would become essential in understanding nuclear fusion in stars. Within the Sun's core, positively charged nuclei must come close enough for the strong nuclear force to bind them together. Classical physics predicts that the electrostatic repulsion between these nuclei should prevent fusion at the relatively low temperatures observed in the Sun. Yet fusion occurs because tunneling allows nuclei to probabilistically overcome the barrier, enabling the reactions that power the Sun and, by extension, life on Earth. Tunneling is also the foundation for a remarkable array of modern technologies. In the microelectronics that underpin computers and smartphones, tunneling allows electrons to move across barriers within semiconductors, enabling the creation of tunnel diodes and the precise control of current at the nanoscale. Scanning tunneling microscopes, which can visualize individual atoms, exploit the effect to produce images with astonishing resolution. Even in chemical and biological processes, tunneling plays a role. Electrons and protons can transfer between molecules more quickly than classical physics would allow, facilitating reactions essential for life. Without this hidden ability, much of modern science and technology would be impossible. The philosophical implications are equally profound. Quantum tunneling forces us to reconsider the nature of reality itself. It demonstrates that barriers are not absolute at the fundamental level, and that matter can behave in ways that defy classical intuition. It shows that the universe is probabilistic rather than deterministic, governed not solely by rigid laws, but also by the interplay of chance and probability. Particles passing through walls challenge our everyday perceptions, revealing a reality far stranger than anything we encounter in daily life. It is remarkable to think that phenomena so alien to our senses are not just theoretical curiosities, but active components of the universe's functioning. Each time an electron tunnels through a potential barrier, a reaction occurs in a star, or a particle escapes a nucleus. The universe reminds us of its hidden complexity. The walls we consider solid and impenetrable are, at the quantum level, permeable, offering particles the freedom to defy expectations and traverse regions that classical physics would deem forbidden. Even the smallest barrier is not absolute. In laboratories around the world, experiments with nanostructures demonstrate tunneling with startling clarity. Electrons move through insulating layers, giving rise to measurable currents that would be impossible if classical rules held. These observations are not anomalies, but consistent results predicted by the mathematics of quantum mechanics. The world of the very small operates according to principles that are elegant, subtle, and deeply counterintuitive, allowing particles to cheat their way across barriers with a hidden agility that seems almost magical. This hidden ability reshapes our understanding of the universe. It blurs the line between what is possible and impossible, showing that even in the presence of obstacles, nature can find a way. Tunneling illustrates that the world at its most fundamental level is not rigid and predictable, but fluid, probabilistic, and full of surprises. It is a reminder that reality is far stranger than our senses suggest, and that the rules governing the macroscopic world are only approximations of deeper, more mysterious principles. In contemplating quantum tunneling, we are forced to expand our imagination. We are invited to consider a universe where particles move through walls, energy barriers are not absolute, and probability reigns supreme. This phenomenon is not just a scientific curiosity, but a window into the hidden workings of reality. It is evidence that the universe contains layers of complexity beyond what we can perceive, where matter can act in ways that defy intuition, and where even the most solid, seeming boundaries can be surmounted in the quiet, probabilistic dance of the quantum world. Quantum tunneling is a reminder that reality is not always what it seems. Walls are not barriers, but challenges to be navigated probabilistically. Obstacles to be overcome not through brute force, but through subtle, hidden possibilities. In this hidden ability, we find both the power of the quantum world and a profound lesson. The universe is far richer, stranger, and more wondrous than the limits of our classical intuition might ever allow. In the quantum realm, particles are not simply tiny, solid points traveling predictably through space. They are far stranger than anything we experience in daily life. To understand how particles can sometimes appear on the other side of barriers, as if slipping through walls, we must first embrace the dual nature of their existence. Particles are simultaneously both waves and particles, a concept so counterintuitive that even the greatest minds struggled to accept it when it was first discovered. This wave-particle duality is one of the foundational pillars of quantum mechanics, and it explains why matter behaves in ways that defy classical intuition. Consider a beam of light passing through a pair of slits, the famous double-slit experiment. When light behaves as a particle, it seems to travel in straight lines, hitting a screen behind the slits in distinct spots. When light behaves as a wave, it spreads out, interfering with itself to create a pattern of alternating bright and dark bands. What amazed physicists was that even when individual photons of light were sent one at a time, over time, the interference pattern still emerged. Each photon, though traveling alone, behaved as if it had passed through both slits simultaneously, as a wave of probabilities. This experiment shattered the classical understanding that objects have definite positions and paths at all times. Particles at the quantum level cannot be described merely as points. They exist as clouds of potential spreading across space, with a probability of being found in any location where the wave allows them to appear. Electrons, protons, and even larger particles, such as atoms, have shown the same duality. When electrons are fired through slits or around obstacles, they create interference patterns characteristic of waves, even though they are traditionally thought of as particles with mass and charge. This duality is not just an abstract idea. It is a measurable reality. It demonstrates that at the quantum level, particles are not simply things. In the classical sense, they are probability distributions, existing as potentialities rather than certainties until they are observed. The act of observation collapses the wave of possibilities into a single outcome, forcing the particle to take on a definite position. Before measurement, however, the particle's location is fundamentally indeterminate, spread out across the landscape of space in a manner governed by the mathematics of the wave function. This wave-like nature of particles is precisely what allows them to tunnel through barriers. In classical terms, a particle approaching a wall with insufficient energy should bounce back. It does not have the required force to climb over or penetrate the barrier. In the quantum world, however, the particle's wave function extends beyond the wall, decaying exponentially but never vanishing entirely. The particle has a finite probability of appearing on the other side, not because it climbed over the barrier or broke through it, but because the wave nature of its existence allows it to explore regions that are forbidden in classical mechanics. The particle behaves as a wave of potential, and when that wave extends past the barrier, it opens the door to the improbable yet real phenomenon of tunneling. This duality challenges the very idea of what it means to be a particle. Classical physics demands certainty. An object occupies one position at one time and follows a predictable trajectory. Quantum physics replaces certainty with probability. The electron is not simply somewhere on one side of a barrier. It has a distribution of possible locations, some of which extend across the barrier. This perspective requires a radical shift in thinking. The particle is not a tiny billiard ball, but a manifestation of a deeper reality, governed by probabilities, wave functions, and potential outcomes. It is neither here nor there until measured. It exists in a state of quantum superposition, a mixture of possibilities that only collapses into a definite reality upon interaction with the outside world. The mathematics behind this duality is elegant yet abstract. The Schrödinger equation, for instance, governs the evolution of a particle's wave function over time, determining how the probability distribution changes in response to forces and barriers. The wave function can interfere with itself, decay, or even resonate in ways that classical particles never could. When encountering a barrier, the Schrödinger equation predicts the amplitude of the wave on the far side, allowing physicists to calculate the probability that the particle will tunnel through. This probability depends on the height and width of the barrier as well as the energy of the particle, but crucially, it is never strictly zero. Even when the odds are vanishingly small, the possibility remains, highlighting the profound flexibility of quantum entities compared to their classical counterparts. This way, particle duality is not limited to exotic experiments or theoretical calculations. It has practical consequences in the world around us. In electronics, for example, the behavior of electrons in semiconductors cannot be understood without acknowledging their wave, like nature. Electrons can leak across barriers, enabling the operation of tunnel diodes and quantum transistors. In chemistry, the wave properties of electrons explain why atoms form bonds in specific ways, and why electrons can transfer between molecules through mechanisms that classical physics would deem impossible. Even in biological systems, certain enzyme reactions are influenced by tunneling effects, where electrons or protons move in ways that rely on their dual nature as both particles and waves. The hidden ability of matter to act as a wave underlies the architecture of the universe, from the tiniest chemical reactions to the design of advanced technology. One of the most striking consequences of wave-particle duality is its philosophical impact. It forces us to reconsider the nature of reality itself. In the macroscopic world, we are accustomed to thinking in absolutes. Things exist in definite places, objects follow predictable paths, and cause and effect rules dominate. The quantum world defies these intuitions. Particles exist as probabilities, as clouds of potential that can interfere, tunnel, and even appear to be in two places at once. Observation plays a crucial role in shaping reality, collapsing the cloud of possibilities into a single outcome. Reality is not fixed and deterministic at its core. It is fluid, probabilistic, and influenced by the very act of measurement. Wave-particle duality also provides a framework for understanding the mysteries of the microscopic world. Without this principle, phenomena like tunneling would be inexplicable. A particle appearing on the other side of a barrier is no longer magic or a violation of physical law. It is the natural consequence of a reality in which entities are not confined to a single trajectory but exist as extended probabilities. The particle explores the barrier not physically but probabilistically, and when conditions align, it emerges on the far side. This is why electrons can move through barriers in a semiconductor, why nuclei in stars can fuse despite seemingly insurmountable electrostatic forces, and why the quantum world exhibits behaviors that defy classical logic. Historically, accepting wave-particle duality required a dramatic shift in thinking. Albert Einstein, Niels Bohr, Louis de Broglie, and Werner Heisenberg each contributed to unraveling this paradoxical nature of matter. De Broglie proposed that all matter exhibits wave-like properties, and experiments with electron diffraction later confirmed this hypothesis. Bohr and Heisenberg formulated the principles of quantum mechanics, introducing concepts such as superposition and uncertainty that provided a coherent framework for understanding wave-particle duality. Einstein's work on the photoelectric effect demonstrated that light, too, has particle-like properties, showing that duality is not limited to electrons or atomic particles, but is a universal characteristic of matter and energy. In contemplating wave-particle duality, one realizes that the universe at its most fundamental level is governed by principles that stretch human imagination. Particles are not static, indivisible points, but dynamic manifestations of probability, capable of behaving as waves when conditions demand. This dual nature explains how the quantum world can produce phenomena that appear impossible: tunneling, interference, and other behaviors that classical physics cannot predict. It reveals a universe where certainty is replaced by possibility, rigidity gives way to fluidity, and barriers are never absolute. The particle's ability to act as a wave allows it to explore spaces, interact in unexpected ways, and perform feats that seem almost magical from a macroscopic perspective. Ultimately, wave-particle duality teaches us to rethink our notions of reality, existence, and causality. It reminds us that the world is not always what it seems, and that at the smallest scales, matter is not a collection of discrete objects, but a continuous tapestry of probabilities, potentialities, and hidden abilities. By understanding this duality, we gain insight into the mechanisms that allow particles to tunnel through barriers, into the operations of technology and life, and into the profound, subtle structure of the universe itself. Particles are not merely present, they are possibilities. They are waves of probability, exploring, interacting, and sometimes defying the walls that classical physics insists should be insurmountable. It is this wave-like quality, this probabilistic existence, that lies at the heart of the hidden abilities of matter, revealing a universe more astonishing, flexible, and mysterious than our everyday experience could ever suggest. In our everyday experience, the world seems governed by rules that are absolute and unyielding. A wall is solid, a locked door cannot be opened without a key, and a hill too steep cannot be climbed without enough energy. Objects obey these constraints predictably, reflecting the classical mechanics of Newton, where mass, force, and energy determine outcomes with certainty. If you want to roll a ball over a ramp, the height of the ramp and the velocity of the ball dictate whether it will succeed or fail. There is no ambiguity. If the ball lacks sufficient speed, it cannot reach the top. Classical physics provides this sense of security and predictability, and it works remarkably well in the macroscopic world of daily life. Yet, when we examine the world at the microscopic scale, these rules start to unravel, revealing a universe far stranger and more flexible than our intuition allows. Energy, in classical terms, is the currency of action. To surmount an obstacle, an object must possess enough energy to overcome it. Consider a simple example: a ball approaching a wall. If the ball does not have sufficient kinetic energy to penetrate the wall or rise over it, it will bounce back. The wall represents a barrier that is absolute, unyielding, and impassable unless the energy threshold is met. This principle extends to nearly all classical systems. Bridges collapse under loads exceeding their design limits. Chemical reactions fail to occur without the necessary activation energy. Celestial bodies follow orbits determined precisely by gravitational energy. The notion of a barrier is intuitive, measurable, and predictable in this context. Energy must match the challenge for progress to occur. However, in the quantum world, the relationship between energy and barriers is not so rigid. At the level of atoms and subatomic particles, energy alone does not dictate absolute outcomes. A particle approaching a barrier that, by classical reckoning, it does not have the energy to overcome can still appear on the other side. The universe at this scale operates on probabilities rather than certainties, governed by the mathematical principles of quantum mechanics. The concept of a barrier is no longer absolute. It is a region where the likelihood of finding a particle diminishes rather than drops to zero. Even when a particle lacks the energy to climb over the barrier, there is a finite chance that it will emerge beyond it, a phenomenon unimaginable in classical physics, but repeatedly verified in quantum experiments. This discrepancy arises from the fundamental differences in how energy operates at the microscopic versus macroscopic scale. In classical mechanics, energy is straightforward. A particle either has enough or it does not. If a hill is higher than the ball can reach, the ball will not crest the hill. The rules are deterministic. Outcomes are predictable. In the quantum domain, energy interacts with the wave-like nature of particles. A particle is not a single point, but a wave function spread across space, describing the probability of its location and momentum. When this wave encounters a barrier, it does not stop abruptly. Part of the wave extends into and even beyond the barrier, decaying in intensity but never completely vanishing. This extension allows for the possibility that the particle can tunnel through, effectively bypassing the classical limit imposed by insufficient energy. One way to visualize this is to imagine a gentle ripple in water approaching a small wall. While most of the ripple will reflect off the wall, a tiny portion may pass over or around it. In classical physics, the ripple represents a particle with insufficient energy, and the wall is impassable. In quantum mechanics, the wave function of the particle allows a similar extension into forbidden territory, offering a non-zero chance that the particle will appear on the other side. This is why phenomena such as tunneling exist. Barriers that seem absolute from a classical perspective are only probabilistically limiting in the quantum world. Energy, while still important, no longer serves as an inviolable gatekeeper. The limits imposed by classical physics are intimately tied to scale. For macroscopic objects, the probability of quantum tunneling is vanishingly small, essentially zero. A baseball or a car cannot pass through a wall because the wave function for an object of such size is concentrated overwhelmingly in one location, and the probabilities of appearing on the other side of a barrier are astronomically small. The energy scales involved make tunneling for large objects practically impossible. Light, while massless, also adheres to classical constraints in certain contexts. Photons cannot penetrate opaque materials unless they are absorbed, reflected, or otherwise manipulated. The distinction lies in the interplay between energy, size, and wave-like behavior. Microscopic particles, with their small masses and wave functions that extend over regions comparable to barrier widths, can exploit quantum probabilities in ways macroscopic objects cannot. Understanding energy barriers in quantum mechanics requires a careful examination of the mathematical framework that governs them. The Schrödinger equation allows physicists to calculate the probability amplitude of a particle's wave function on the far side of a barrier. The height of the barrier relative to the particle's energy and the barrier's thickness determine how rapidly the wave function decays. The thicker and taller the barrier, the smaller the probability of tunneling, yet it is never zero. Even particles with energies far below the classical threshold have a non-zero chance of passing through. This mathematical description transforms the concept of energy barriers from an absolute restriction to a probabilistic challenge, where success is measured not by deterministic energy thresholds, but by the subtle interplay of wave function, decay, and quantum probability. The implications of these principles are profound and far-reaching. In technology, understanding energy barriers and their quantum permeability allows engineers to design devices at the nanoscale. Semiconductors, transistors, and tunnel diodes rely on the controlled manipulation of electrons across barriers that classical physics would predict as insurmountable. Without acknowledging the quantum nature of energy and barriers, these innovations would be impossible. Even more remarkably, nuclear fusion in stars relies on tunneling to overcome energy barriers. Protons in the Sun's core face immense electrostatic repulsion, far greater than their thermal energies should allow them to overcome. Classical physics predicts that fusion should be extremely rare or impossible at the Sun's temperatures. Yet fusion occurs because tunneling allows protons to probabilistically penetrate the repulsive barrier, releasing the energy that powers the Sun and sustains life across the solar system. Energy barriers are also central to understanding chemical reactions. Many reactions require an activation energy to proceed, a classical barrier that molecules must overcome to react. At low temperatures, classical physics predicts that reactions will not occur if molecules lack sufficient kinetic energy. Yet quantum tunneling allows electrons, and sometimes even nuclei, to traverse these barriers probabilistically, enabling reactions at rates that classical models cannot explain. Enzymatic reactions in living cells, for instance, often exploit tunneling to facilitate electron and proton transfers, allowing life to proceed efficiently in conditions that would otherwise seem restrictive. The hidden ability of particles to bypass energy barriers at the quantum level is not a theoretical curiosity. It is a fundamental component of the processes that shape the natural world. Philosophically, the contrast between classical limits and quantum probabilities challenges our assumptions about certainty, causality, and the nature of reality. Classical physics gives the illusion of a rigid, predictable universe where energy strictly governs outcomes. Quantum mechanics reveals that the universe is far more flexible, with energy barriers that are permeable in subtle but profound ways. A particle approaching a wall with insufficient energy does not simply fail. It may succeed, not by brute force, but by the hidden probabilities encoded in its wave function. This insight forces us to reconsider the meaning of impossibility, and to acknowledge that reality, at its most fundamental level, operates according to principles that defy everyday intuition. Even as the principles of classical mechanics remain accurate for macroscopic objects, energy barriers in the quantum world reveal a layer of the universe that is hidden from direct perception. The solidity we perceive, the walls and obstacles that seem absolute, is an emergent property of averaging over countless quantum particles. At the microscopic level, matter is far more fluid, dynamic, and probabilistic. Energy barriers, while still relevant, do not act as absolute gates. Instead, they define regions where the likelihood of certain outcomes changes, creating a universe in which the improbable can and does occur, shaping both the natural and technological world. This understanding also underscores the remarkable precision required in experiments and technologies that exploit quantum effects. The height, width, and composition of barriers must be carefully controlled to achieve desired probabilities. Electrons must be guided, barriers engineered, and energies finely tuned to ensure that tunneling occurs with predictable outcomes. By mastering these subtleties, scientists and engineers harness the hidden abilities of particles, transforming what seems impossible into practical applications. This mastery illustrates the deep interplay between energy, probability, and wave behavior, and highlights the remarkable ways in which the universe allows matter to transcend the classical limit that once seemed inviolable. In contemplating energy barriers and classical limits, one is struck by the elegance and subtlety of the universe. What appears absolute at one scale becomes permeable at another. What is impossible in our macroscopic experience is routine at the quantum level. Particles navigate barriers not through brute force, but through the probabilistic nature of their existence, exploiting the hidden flexibility of reality. The classical world, with its rigid energy thresholds, is merely an approximation of a deeper, more nuanced framework in which possibility, probability, and wave-like behavior govern outcomes. Energy barriers, far from being walls that strictly define what can or cannot occur, are windows into the quantum nature of the universe. They reveal a world in which particles can defy expectations, explore forbidden regions, and accomplish feats unimaginable to classical intuition. The concept of energy as an absolute gatekeeper dissolves at the microscopic scale, replaced by a nuanced interplay of probabilities, wave functions, and quantum laws. In this hidden flexibility lies the power to explain tunneling, nuclear fusion, chemical reactions, and countless technological innovations. The universe, it seems, is far more subtle, strange, and wondrous than the rigid rules of classical physics might suggest. The strange, almost magical ability of particles to pass through barriers is not merely an observation of nature. It is a phenomenon that can be described, predicted, and quantified using the elegant mathematics of quantum mechanics. At first glance, the idea that a particle could appear on the other side of a wall it seemingly cannot cross might seem impossible, even miraculous. Yet the reality of quantum tunneling is firmly grounded in mathematical principles that have been tested and verified in countless experiments. The mathematics transforms what seems like magic into something understandable, albeit profoundly counterintuitive, revealing the hidden structure of the universe at its smallest scales. At the heart of this description is the wave function, a mathematical expression introduced by Erwin Schrödinger in the 1920s. The wave function encodes everything that can be known about a particle: its position, momentum, energy, and the probabilities of finding it in various locations at any given time. Unlike a classical particle, which occupies a single point in space with certainty, a quantum particle is represented by a wave spread over a region. This wave is not a physical ripple in space, but a probability wave, a measure of where the particle might be observed. The amplitude of the wave at a particular location corresponds to the likelihood of finding the particle there, while the square of that amplitude gives the probability density. The mathematics of tunneling arises from analyzing how this wave function behaves when it encounters an obstacle. When a particle approaches a barrier, the Schrödinger equation governs how the wave function evolves. The barrier can be thought of as a region where the potential energy rises above the particle's kinetic energy. In classical terms, this is insurmountable. The particle does not have enough energy to climb the barrier and should reflect back. In quantum mechanics, however, the wave function does not terminate abruptly at the barrier. Instead, it gradually decays within the barrier, decreasing exponentially as the particle moves deeper into the forbidden region. Mathematically, the wave function inside the barrier takes the form of an exponentially decaying function, rather than an oscillating wave. This decay represents the decreasing probability of finding the particle within the barrier, but crucially, it never reaches zero. As long as there is a non-zero amplitude on the far side of the barrier, there is a finite probability that the particle will appear there. This is the essence of tunneling. The wave function allows the particle to exist in regions that would be strictly forbidden in classical physics. The probability of tunneling can be calculated using the mathematics of the wave function and the properties of the barrier. For a simple one-dimensional barrier, the height and width of the barrier, along with the particle's energy, determine how rapidly the wave function decays inside it. The higher and wider the barrier, the smaller the probability that the particle will emerge on the other side, because the wave function diminishes more before reaching the exit. The formula governing this decay shows an exponential dependence. A modest increase in barrier width or height can dramatically reduce the tunneling probability. Conversely, even a particle with energy below the barrier has a chance, however small, to appear on the far side. This exponential relationship is at the core of many quantum phenomena, explaining why tunneling is rare in some cases and common in others. One of the earliest and most striking confirmations of the mathematics of tunneling came from the study of alpha decay in radioactive nuclei. Atomic nuclei contain positively charged protons and neutrons bound together by the strong nuclear force. Yet some nuclei spontaneously emit alpha particles, clusters of 2 protons and 2 neutrons, even though the energy of the alpha particle is insufficient to overcome the electrostatic repulsion of the nucleus. According to classical physics, the solution lay in quantum mechanics. The wave function of the alpha particle extends beyond the nuclear barrier, and the probability of finding it outside the nucleus corresponds precisely to the rate of radioactive decay observed. Experimentally, without the mathematics of tunneling, there would be no explanation for this phenomenon. It is not chance alone. It is the predictable outcome of a wave function interacting with a barrier, governed by equations that describe the probabilities of quantum events. The same mathematics underlies the behavior of electrons in modern electronics. In semiconductors and tunnel diodes, electrons encounter energy barriers formed by insulating layers or potential differences. Classical physics would predict that these electrons should remain confined unless they possess sufficient energy to overcome the barrier. Quantum mechanics, through the wave function, allows electrons to tunnel across barriers even when their energies are insufficient. The probability of tunneling determines the current that flows through the device, enabling engineers to design highly precise and efficient electronic components. In this way, the mathematics of tunneling translates directly into technological innovation, allowing abstract equations to govern tangible, real-world behavior. The Schrödinger equation, while abstract, can also be used to model more complex systems beyond simple one-dimensional barriers. For example, it can describe electrons tunneling through potential wells in atoms or molecules, or protons tunneling in chemical reactions within biological systems. In each case, the principle remains the same. The wave function decays in regions of higher potential energy, and the probability of observing the particle on the other side is finite. By solving these equations for specific barriers, physicists can predict reaction rates, tunneling currents, and even nuclear fusion probabilities. The mathematics provides not only a descriptive tool, but also a predictive one, allowing researchers to explore phenomena that are otherwise impossible to observe directly. A crucial aspect of this mathematics is its probabilistic nature. Unlike classical equations, which yield exact results, the Schrödinger equation provides probabilities of outcomes. The particle does not choose to tunnel or not in a deterministic sense. The wave function describes the likelihood of different possibilities. When a measurement is made, the wave function collapses, and the particle appears in a definite location. This probabilistic framework is counterintuitive because it contradicts our macroscopic experience, where objects follow predictable paths. Yet, at the microscopic level, probability is the only language capable of describing reality accurately. The mathematics formalizes this probabilistic world, quantifying the odds of events that defy classical expectations. The mathematics of tunneling also reveals fascinating limits and thresholds. Barriers that are extremely thick or high result in probabilities that are exponentially small, essentially preventing tunneling in practical terms. Conversely, thin or low barriers allow for relatively high probabilities, leading to observable effects. This sensitivity to barrier properties explains why tunneling is common in some quantum systems and rare in others. It also underscores the delicate interplay between energy, barrier characteristics, and wave function decay, a relationship that can be manipulated in laboratories to control quantum behavior with remarkable precision. Beyond its practical and experimental significance, the mathematics of tunneling illuminates the nature of the universe itself. It shows that barriers, which seem absolute in classical terms, are merely probabilistic boundaries in the quantum realm. Energy thresholds are no longer strict limits, but parameters that influence probabilities. Particles navigate these barriers not by brute force, but by exploiting the inherent flexibility of their wave functions. The universe at this scale is not deterministic in the classical sense. It is a landscape of possibilities, governed by equations that allow for outcomes once considered impossible. The mathematics transforms mystery into understanding, providing a framework in which phenomena like tunneling are not only possible but predictable. Finally, the elegance of this mathematical framework lies in its universality. It applies to electrons in semiconductors, protons in stellar cores, alpha particles in radioactive nuclei, and even larger quantum systems under certain conditions. The same equations that describe the probability of an electron tunneling through an insulating barrier also predict the fusion reactions in the Sun and the behavior of particles in cutting edge quantum technologies. This universality reflects a deep harmony in nature. The hidden abilities of particles, the permeability of barriers, and the probabilistic structure of reality are all manifestations of a coherent mathematical framework that spans the smallest to the largest scales. Through this mathematics, what initially seems impossible, the passage of a particle through a barrier it cannot classically overcome, becomes understandable, predictable, and even controllable. The equations give shape to the strange, probabilistic nature of the quantum world, revealing that reality is far more flexible and surprising than our classical intuition would suggest. Tunneling is no longer a mysterious exception. It is the natural consequence of a universe governed by probabilities, wave functions, and the subtle interplay of energy and potential. The mathematics transforms the hidden ability of particles into a comprehensible, almost tangible truth, showing us that the universe operates according to principles far stranger and more elegant than the macroscopic world would lead us to believe. The hidden ability of particles to pass through barriers is not merely a theoretical curiosity or a thought experiment for physicists. It has practical consequences that touch nearly every aspect of modern technology and scientific exploration. This remarkable phenomenon, known as quantum tunneling, underpins some of the most transformative innovations in electronics, computing, and even medicine. What once seemed impossible, the notion that a particle could traverse a barrier it lacked the energy to overcome, has become the cornerstone of devices and processes that define our technological age. Consider the world of electronics, where the movement of electrons through materials governs the operation of every device, from smartphones to supercomputers. Classical physics would suggest that electrons cannot cross insulating layers or energy barriers unless they possess sufficient energy. Yet in the quantum realm, electrons exploit their wave, like nature, to tunnel across these barriers, allowing current to flow in ways that classical mechanics cannot predict. The tunnel diode, for example, is a device that relies entirely on this principle. Unlike conventional diodes, which permit current in one direction once a voltage threshold is exceeded, tunnel diodes exploit the tunneling effect to allow electrons to cross a barrier even when they lack the classical energy required. This results in extraordinarily fast electronic responses, enabling applications in high-frequency circuits and advanced signal processing. Transistors, the fundamental building blocks of modern electronics, also benefit from tunneling effects. At the nanoscale, where components are only a few atoms thick, the quantum behavior of electrons becomes significant. Designers must account for the probability that electrons can tunnel through barriers, which influences leakage currents and device performance. By understanding and controlling tunneling, engineers can create transistors with precise characteristics, improving the speed, efficiency, and reliability of computers and other digital devices. In this way, a phenomenon that seems esoteric and counterintuitive has become a practical tool, allowing humanity to harness the hidden rules of the quantum world for everyday technological advancement. Quantum tunneling also plays a critical role in memory storage devices. Flash memory, which powers smartphones, USB drives, and solid-state drives, relies on the controlled movement of electrons through insulating barriers. By exploiting tunneling, memory cells can store charges in specific locations, encoding information that persists even when the device is powered off. This capability would be impossible without the subtle interplay of energy, wave functions, and tunneling probabilities. What seems like a minor quantum effect at the particle level becomes, at the scale of billions of electrons, a reliable and reproducible means of storing information, illustrating how the principles of the microscopic world scale up to tangible technological benefits. Beyond electronics, tunneling has revolutionized the field of imaging and microscopy. The scanning tunneling microscope, STM, developed in the 1980s, allows scientists to visualize individual atoms with unprecedented resolution. The STM works by bringing a sharp metallic tip extremely close to a conductive surface. Electrons tunnel between the tip and the surface, generating a current that varies with distance. By scanning the tip across the surface and measuring the tunneling current, scientists can construct detailed images of atomic arrangements. This is not merely an impressive feat of engineering. It has opened new frontiers in materials science, nanotechnology, and condensed matter physics. Researchers can manipulate individual atoms, explore the electronic properties of novel materials, and design structures at the atomic level. All because tunneling makes it possible to detect electrons in ways that classical physics would deem impossible. In the field of medicine, tunneling has enabled remarkable diagnostic and therapeutic tools. Magnetic resonance imaging (MRI) and other imaging technologies, while primarily relying on nuclear magnetic properties, benefit indirectly from our understanding of quantum behavior. More directly, tunneling principles inform the operation of certain types of sensors, electron microscopy techniques, and advanced molecular imaging devices. These tools allow physicians to observe cellular and molecular structures with extraordinary precision, detecting diseases at their earliest stages. Quantum tunneling thus bridges the gap between the microscopic behavior of particles and the macroscopic needs of medicine, demonstrating that even the most subtle quantum effects can have life-saving applications. Quantum tunneling is also central to understanding and advancing energy technologies. In nuclear fusion, the process that powers stars, tunneling allows positively charged nuclei to overcome their electrostatic repulsion, combining to release enormous amounts of energy. Efforts to replicate fusion on Earth for clean and virtually limitless power depend on this principle. Even though the nuclei may not have sufficient kinetic energy to classically overcome the Coulomb barrier, tunneling provides a probabilistic pathway that makes fusion feasible. By harnessing this hidden ability, scientists aim to develop energy solutions that could transform human civilization, reducing reliance on fossil fuels and providing sustainable power. In addition to energy, tunneling plays a role in chemical catalysis and biological processes. Enzymes, the molecular machines that drive life, often facilitate reactions that involve the transfer of electrons or protons through barriers that classical chemistry would deem insurmountable. These reactions occur faster than expected because particles can tunnel between locations, lowering the effective energy required and speeding up chemical transformations. Understanding tunneling in these contexts is not merely academic. It informs drug design, the development of synthetic enzymes, and even the creation of artificial photosynthetic systems. Renewable energy. Quantum tunneling reveals itself as a hidden facilitator of life itself, connecting the principles of subatomic physics to the complexity of biological systems. Another fascinating technological application lies in the realm of quantum computing. Quantum bits, or qubits, rely on the principles of superposition and tunneling to store and manipulate information in ways that classical bits cannot. Electrons or other particles in a qubit can exist in multiple states simultaneously, and tunneling allows them to transition between energy levels or quantum states without the constraints imposed by classical energy barriers. This capability enables quantum computers to perform calculations exponentially faster than conventional machines for certain problems, promising breakthroughs in cryptography, optimization, and material science. Tunneling is not just a theoretical curiosity in this context. It is an operational principle that underpins the next generation of computational technology. Even in the realm of sensing and measurement, tunneling has made profound contributions. Devices that exploit tunneling currents can detect changes at the atomic or molecular level, allowing for sensors of extraordinary sensitivity. This includes chemical sensors capable of detecting minute concentrations of substances, as well as magnetic sensors used in navigation, medical diagnostics, and industrial applications. By observing how particles tunnel under controlled conditions, scientists can detect minute changes in the environment, creating technologies that were unimaginable before the quantum revolution. What emerges from these applications is a striking truth. The hidden ability of particles to tunnel through barriers connects the abstract and microscopic world of quantum mechanics with tangible, macroscopic outcomes. The wave-like nature of particles, the probabilistic framework of quantum mechanics, and the mathematics that describe tunneling all converge to enable technologies that shape modern life. From electronics to medicine, from energy generation to quantum computing, this once mysterious phenomenon has become an essential tool, revealing how the principles of the universe at its smallest scales can be harnessed for practical purposes. Beyond practical applications, the technological implications of tunneling also highlight a profound philosophical insight. What seems impossible in classical terms, the passage of a particle through a barrier, becomes not only possible, but useful in shaping the world around us. Humanity's ability to exploit quantum tunneling demonstrates the power of understanding and embracing the hidden laws of nature. By mastering the probabilistic and counterintuitive behavior of particles, we gain control over phenomena that would otherwise remain inaccessible, unlocking innovations that redefine what is technologically achievable. Ultimately, the applications of tunneling in technology and medicine are more than just demonstrations of scientific curiosity. They are evidence of the deep connection between fundamental physics and the practical world. Electrons passing through insulating barriers enable the devices we rely on every day. Nuclei tunneling in stars power the sunlight that sustains life. Tunneling in enzymes allows biological systems to function efficiently. This hidden ability bridges scales and disciplines, showing that the strange, counterintuitive rules of quantum mechanics are not confined to laboratories, but are active, indispensable components of the natural and technological world. Through electronics, imaging, energy, medicine, and quantum computing, tunneling transforms the improbable into the routine. It allows engineers, scientists, and physicians to design devices and systems that operate with precision and efficiency unimaginable under classical rules. The mathematics, the probability waves, and the wave-particle duality all converge to create a framework in which these hidden abilities of particles are not only observable but exploitable, demonstrating the profound utility of quantum phenomena in shaping the modern world. In contemplating the technological applications of tunneling, one recognizes the remarkable interplay between theory and practice. What began as a puzzling quantum observation has become the foundation for entire industries and revolutionary scientific instruments. The hidden ability of particles to bypass energy barriers has empowered humanity to manipulate matter at the smallest scales, to see the invisible, to compute faster, and to probe the very fabric of reality. It is a testament to the power of scientific insight. By understanding the rules of the quantum world, we can unlock capabilities that once seemed impossible, transforming abstract principles into tangible benefits that enrich every aspect of human life. Quantum tunneling is not simply a curiosity confined to textbooks. It is a dynamic and practical force that shapes modern science and technology. From the flow of electrons in microchips to the fusion of nuclei in stars, from imaging individual atoms to enabling life itself at the molecular level, tunneling illustrates the profound consequences of the hidden abilities of particles. The universe, in its most fundamental layers, offers pathways that classical physics cannot explain, and humanity, through careful observation and mathematical understanding, has learned to navigate these pathways, creating a technological and scientific revolution built on the extraordinary, counterintuitive nature of quantum reality. Quantum tunneling is often discussed in laboratories or in the context of electronics, but the implications of this hidden ability extend far beyond human-made devices. In nature, it is a subtle yet fundamental process that governs phenomena on scales ranging from the cores of stars to the molecular machinery of life itself. What seems impossible from a classical standpoint, the passage of particles through energy barriers they cannot classically overcome, is, in fact, a central mechanism in the universe, quietly enabling processes that sustain the cosmos and the living world. Consider the Sun, a seemingly ordinary star in our night sky. At its core, the Sun is a seething sphere of hydrogen gas at millions of degrees, where temperatures and pressures are enormous. Here, nuclear fusion occurs. Hydrogen nuclei collide and combine to form helium, releasing enormous amounts of energy in the form of light and heat. Classical physics suggests that the positively charged nuclei of hydrogen should repel each other so strongly that fusion would be improbable at the temperatures present in the Sun's core. The electrostatic Coulomb barrier, which arises from the repulsion between like charges, appears insurmountable. Yet fusion occurs with astonishing regularity, powering the Sun and providing the energy necessary for life on Earth. The explanation lies in quantum tunneling. The nuclei in the Sun do not behave like tiny billiard balls colliding in predictable trajectories. Instead, they exist as quantum particles with wave functions that spread over space. These wave functions allow the nuclei to probabilistically penetrate the electrostatic barrier, even when their thermal energies are below the classical threshold. The mathematics of tunneling predicts the probability that two nuclei will overcome the barrier and fuse, and remarkably, the calculated rates match observational data of stellar energy output. Without tunneling, stars like the Sun would burn far less efficiently or not at all, and the universe would be a very different place. It is the hidden ability of particles to traverse energy barriers that makes stellar fusion possible, sustaining the light, heat, and life that we take for granted. Tunneling in stars is not limited to hydrogen fusion. In more massive stars, heavier nuclei also undergo fusion processes that involve tunneling. Carbon, oxygen, and heavier elements form in stellar cores through reactions that would be classically forbidden at the temperatures and pressures present. The production of these elements, which later seed planets and life, is directly tied to the probabilistic nature of quantum tunneling. The universe's chemical diversity, the very elements that make up our bodies, our planet, and the Earth's atmosphere, exists in part because particles can defy classical energy limits. Without this phenomenon, the cosmos would remain a simpler, less hospitable place, devoid of the complexity necessary for stars, planets, and life to develop. On a much smaller scale, tunneling is just as vital to life itself. Biological systems operate at the molecular level, where electrons and protons must move between molecules to facilitate chemical reactions. In many enzymatic reactions, particles must traverse energy barriers that are too high for classical motion alone. Quantum tunneling provides a mechanism by which these reactions occur efficiently at physiological temperatures. Enzymes, the molecular machines that accelerate chemical reactions in cells, exploit tunneling to transfer protons or electrons rapidly and reliably. These transfers allow metabolic pathways to proceed at rates sufficient to sustain life, underpinning processes such as respiration, photosynthesis, and DNA repair. Without tunneling, the chemistry of life would be vastly slower or even impossible under the conditions present in living organisms. An illustrative example lies in the process of cellular respiration, where electrons are transferred through a chain of protein complexes in mitochondria to produce energy in the form of ATP. Some steps in this electron transfer chain involve tunneling, allowing electrons to move between sites separated by potential energy barriers. Classical physics would predict that these reactions should be too slow at body temperature, but tunneling makes them efficient. Similarly, in photosynthesis, protons and electrons move within protein complexes to convert sunlight into chemical energy. Quantum tunneling is a hidden facilitator of these movements, ensuring that the energy conversion occurs quickly and effectively. Life, in this sense, is built upon the invisible bridge that quantum tunneling provides, linking microscopic particle behavior to macroscopic biological function. Tunneling also explains certain isotopic effects in biology and chemistry. For instance, hydrogen, being a very light atom, is particularly susceptible to tunneling. Reactions involving hydrogen atoms can occur faster than expected because the light particle can penetrate energy barriers more easily than heavier nuclei. This has implications not only for biochemistry, but also for the origins of life, chemical evolution, and the stability of molecules under different environmental conditions. The hidden ability of particles to tunnel shapes the pathways of chemical reactions, influencing which molecules are formed, how they interact, and how energy flows through living systems. Beyond Earth, tunneling may also play a role in the chemistry of other celestial bodies. On icy moons, in interstellar clouds, or within the high-pressure cores of distant planets, reactions can occur at temperatures and energies that are classically insufficient. Tunneling enables these reactions, contributing to the formation of complex molecules and potentially prebiotic compounds. In this sense, quantum tunneling is not merely a terrestrial phenomenon. It is a universal process that shapes the evolution of matter across the cosmos. It is one of the invisible threads that connects the physics of particles to the chemistry of life and the broader dynamics of the universe. The role of tunneling in natural processes highlights the profound interconnectedness of scales. A particle passing through an energy barrier in a microscopic reaction is governed by the same underlying principles as protons in stellar fusion. The mathematics, wave functions, and probabilistic rules that describe tunneling apply equally to these vastly different contexts. This universality underscores the elegance of quantum mechanics. The same hidden ability that allows an electron to navigate a molecular barrier also powers the light of stars and the energy of living cells. It is a unifying principle that bridges physics, chemistry, and biology, revealing the subtle yet powerful ways in which the quantum world shapes the universe. Nature also demonstrates the efficiency and economy of tunneling. By allowing reactions and processes to occur that would otherwise require far higher energies, tunneling conserves energy and enables systems to operate under conditions that are feasible in reality. Stars can fuse nuclei without reaching absurd temperatures. Enzymes can catalyze reactions without excessive heat, and chemical reactions can proceed at room temperature. Tunneling is an invisible facilitator, reducing the energy cost of natural processes while maintaining their functionality. This efficiency has profound implications for both the emergence of life and the sustainability of ecosystems, demonstrating that quantum principles are not abstract curiosities but fundamental enablers of existence. The hidden ability of particles to bypass barriers also prompts reflection on the adaptability and flexibility of natural systems. Nature does not rely solely on brute force or classical energy thresholds. It leverages the subtle, probabilistic behavior of matter to achieve outcomes that would otherwise be impossible. Tunneling illustrates that what may appear as an insurmountable challenge, whether an electrostatic barrier in a star or an activation energy in an enzyme, is not absolute at the microscopic level. Particles exploit the probabilistic rules of quantum mechanics, ensuring that reactions, energy transfer, and fusion occur reliably over time, even in the face of apparent classical limitations. In contemplating natural occurrences of tunneling, one gains a sense of awe at the hidden orchestration of the universe. Stars shine because nuclei can probabilistically penetrate barriers. Life thrives because electrons and protons can traverse molecular landscapes that classical physics would deem forbidding. The universe is full of processes that depend on the subtle, invisible rules of quantum mechanics, where the hidden abilities of particles enable outcomes essential to existence. Tunneling is a reminder that the most fundamental level of reality operates according to principles that defy everyday intuition. Yet these principles are crucial for the very fabric of nature. Ultimately, tunneling in stars and life demonstrates that the universe is not rigidly constrained by classical limits. Energy barriers, while seemingly absolute from a macroscopic perspective, are permeable at the microscopic scale. Probabilities, wave functions, and quantum rules govern the behavior of particles, enabling phenomena that sustain both the cosmos and living systems. The hidden ability of particles to pass through walls, barriers, or obstacles is not merely a theoretical curiosity. It is a fundamental process that makes the universe dynamic, efficient, and capable of supporting complexity. From the fusion that powers the sun to the molecular transfers that power life, quantum tunneling is a silent, pervasive force, quietly shaping the natural world in ways that remain hidden yet absolutely essential. Through this lens, the universe reveals itself as both subtle and resilient. It is a place where the improbable becomes possible, where energy barriers are not final limits, and where life and stars alike depend on the hidden abilities of particles. Quantum tunneling bridges the microscopic and macroscopic, the particle and the cosmos, illustrating that reality is far richer and more astonishing than classical intuition alone could ever suggest. Nature, in its elegance and efficiency, has long exploited the probabilistic world of quantum mechanics, and in doing so, it has harnessed the hidden powers of particles to sustain the universe itself. Quantum tunneling is more than a fascinating scientific phenomenon. It is a window into the underlying nature of reality itself. At first glance, the idea that particles can pass through barriers they do not have the energy to surmount seems almost fantastical, challenging everything we have learned from classical physics. Walls that seem solid, obstacles that appear absolute, and energy limits that should govern behavior are all revealed at the quantum level to be probabilistic rather than definitive. This realization forces a profound reconsideration of the concepts of determinism, causality, and the very nature of existence. Classical physics, from Newton to Maxwell, presents the universe as a machine governed by clear, predictable laws. Objects follow definite paths, collisions are precise, and energy thresholds determine outcomes. From this perspective, barriers are final. If a ball does not have enough kinetic energy to roll over a hill, it simply cannot. The universe appears predictable, orderly, and bound by cause and effect. For centuries, this world, you dominated human understanding, providing the foundation for technology, astronomy, and mechanics. It seemed unshakable, a reflection of how reality must operate. Quantum tunneling disrupts this intuition. Particles, at their most fundamental level, do not have fixed positions or definite energies in the way classical physics demands. They exist as wave functions, mathematical descriptions of probability that spread across space and time. A particle approaching a barrier does not decide to cross in a deterministic sense. Instead, its wave function partially extends into the forbidden region, providing a finite probability of appearing on the other side. In essence, reality is not composed of absolute certainties, but of potentialities that become definite only when measured or observed. The wall, the barrier, and the energy threshold are not insurmountable absolutes, they are regions of varying probability. This insight has profound philosophical implications. If particles can bypass barriers that classical physics deems impossible, what does this say about the limits of causality? At the microscopic level, the universe is not a rigid chain of cause and effect, but a landscape in which outcomes are probabilistic. Determinism, long considered a hallmark of natural law, gives way to uncertainty. The future is not strictly dictated by the past. It is shaped by probabilities and wave functions, with events that may seem improbable becoming real simply because the quantum rules allow them. Tunneling, then, is not merely a particle phenomenon. It is a challenge to the classical conception of reality. The philosophical implications extend to the concept of observation and measurement. In quantum mechanics, the act of observation collapses a particle's wave function into a definite state. Before observation, the particle exists as a superposition of possibilities, each with a corresponding probability. The hidden ability of particles to tunnel through barriers exemplifies this principle. The particle is not physically inside or outside the barrier in a classical sense. It is in a liminal state of potential. Only when measured does it assume a definite position. This challenges the notion of objective reality. Reality, at the quantum level, is intertwined with observation. What we perceive is not independent of the act of measurement, but is partially shaped by it. Tunneling also forces a re-evaluation of what is possible and impossible. In classical terms, a particle lacking sufficient energy cannot pass a barrier period. In quantum mechanics, no barrier is absolute. All are permeable to some degree. The universe is more flexible and more probabilistic than intuition suggests. This has inspired scientists and philosophers alike to reconsider the boundaries of nature, the meaning of limitation, and the relationship between the microscopic and macroscopic worlds. It suggests that reality is not a rigid hierarchy of laws, but a subtle framework of probabilities in which seemingly impossible events can and do occur. The scientific implications are equally profound. Tunneling challenges our ability to predict outcomes with certainty, forcing a shift from deterministic models to probabilistic ones. This does not mean that science loses its predictive power. Rather, it operates within a framework of probabilities that are calculable and reliable at large scales. For example, while we cannot predict when an individual alpha particle will tunnel out of a nucleus, we can predict the decay rate of billions of particles with remarkable precision. Nature's hidden flexibility does not preclude understanding. It requires a more nuanced understanding, one that embraces uncertainty as an intrinsic feature rather than a flaw in knowledge. Tunneling also highlights the interconnectedness of the universe at scales often considered separate. The same principles that govern electrons in a semiconductor apply to nuclei in stars and protons in biochemical reactions. The wave function, the probability distribution, and the tunneling mechanism are universal. This universality challenges the classical notion that different scales of reality obey fundamentally different rules. Instead, it suggests a continuity in the underlying structure of the cosmos, where hidden abilities of particles manifest across physics, chemistry, biology, and even cosmology. It is a reminder that the universe operates according to principles far subtler and more profound than everyday experience would suggest. Philosophically, tunneling invites reflection on the nature of causality, chance, and agency. Events that are highly improbable are nonetheless possible, and in some cases inevitable when considered over sufficient time or large numbers. This probabilistic aspect resonates beyond physics, influencing thinking in fields as diverse as complexity science, evolutionary biology, and even philosophy of mind. The universe is not a rigid machine, but a dynamic interplay of probabilities, where hidden potentialities shape outcomes in ways that defy classical intuition. Tunneling is a microcosm of this principle, a tangible demonstration that the improbable is not impossible and that the universe accommodates pathways that classical reasoning would forbid. Tunneling also emphasizes the limits of human intuition. Our brains evolved to navigate a macroscopic world where objects are solid, energy is conserved in straight, forward ways, and probability plays a minor role. Quantum mechanics, and tunneling in particular, confronts us with phenomena that defy these intuitions. Electrons, protons, and other particles do not behave like miniature versions of macroscopic objects. They obey laws of probability, wave functions, and superposition. Understanding these phenomena requires not only mathematics and experimentation, but a conceptual shift in how we think about reality. It is a humbling lesson that the universe does not conform to our intuitive expectations, but rather operates according to principles that are deeper, stranger, and more elegant than we might imagine. Tunneling also blurs the boundary between the deterministic and the random. While classical physics treats cause and effect as absolute, quantum tunneling demonstrates that outcomes are probabilistic yet constrained by underlying laws. The probability of tunneling can be calculated precisely using the Schrödinger equation, yet the exact moment or position of a particle's emergence remains uncertain until measurement. This interplay between predictability and randomness challenges traditional notions of certainty. It suggests a universe in which structure and chance coexist, where hidden potentialities govern the dynamics of matter and energy. The probabilistic framework of tunneling is a window into this delicate balance, showing how the universe maintains order while embracing uncertainty. In a broader sense, tunneling forces a reconsideration of the boundaries between science and philosophy. The phenomenon is simultaneously a concrete, measurable effect and a conceptual challenge to our understanding of reality. It illustrates that scientific exploration can reveal truths that are not only practical, but also profoundly philosophical. The universe, through the hidden abilities of its smallest constituents, prompts questions about the nature of possibility, the role of observation, and the limits of human understanding. Tunneling exemplifies the intersection of knowledge and wonder, demonstrating that science can expand not only our technological capabilities, but also our conceptual horizons. Ultimately, the hidden ability of particles to bypass barriers reminds us that reality is more flexible, subtle, and interconnected than classical physics would suggest. Walls that appear absolute are permeable at the quantum level. Energy thresholds, once thought inviolable, are probabilistic. Observation, probability, and wave functions all shape outcomes in ways that challenge classical intuition. Tunneling is not merely a curiosity. It is a profound insight into the nature of existence, bridging the microscopic and macroscopic, the possible and the improbable. It is a testament to the universe's complexity, elegance, and capacity for surprise. Through the lens of tunneling, we gain a deeper appreciation for the hidden rules that govern the cosmos. We see that reality is not fixed and deterministic, but probabilistic and subtle, that particles can navigate obstacles in ways that seem impossible, and that these hidden abilities underlie processes as diverse as electronics, biology, and stellar fusion. Quantum tunneling challenges our assumptions, reshapes our understanding of causality, and invites a new perspective on the nature of existence itself. It is a reminder that the universe operates according to principles that are often invisible, profoundly counterintuitive, and yet deeply elegant, revealing a reality that is richer and stranger than we could ever imagine.